Podcasting from Lund, the 11th biggest city in Sweden and the birthplace of the city's first Beatles-esque celebrity, Esaias Tegnér, and also one of the most advanced laboratories in the world, Max 4. This is Intronauts, bringing you inside the Max 4 facility where you get to meet some of the greatest minds and the explorers of tomorrow. I am your host, Toril Kornfeldt, together with Communications Officer Laura Rastar.
Today we're actually at one of the beamlines where the experiments take place. We meet Nønne Prisle, Associate Professor at University of Oulu, who hopes to understand how cloud droplets form and dissolve in order to make better climate models in the future.
So, right now we're standing next to one of the beamlines, along with one of the scientists, Nønne Prisle. It's really nice to be here with you.
Thank you. It's very nice to be here with you.
It's a bit loud here. We're out in the circle at Max 4, and there's a lot of stainless steel things just happening around me. Can you tell me a bit about what we're seeing?
Yeah, so we're standing here at the end of the beamline, and as a user, this is where the action happens for us. So you know that the synchrotron, the ring, generates the light. And the different beamlines are these long tubes that go from the ring and out here. And the beamlines are the optical elements that take the light from the ring to the experiment. So what we do when we come here is that we mount our experimental station at the end of the beamline. The environment allows us to place a sample that intersects with the radiation, so the light, and a detector that we can manipulate our sample with the light, and then we can detect what comes out. And that gives us the result of the experiment.
Would it be possible for you to put in a sample now or do an experiment now?
No, it wouldn't.
Why not?
It's a very long process. I'm an atmospheric scientist, so we try to generate atmospheric samples. We cannot just take the synchrotron and go out and measure in nature. We need to somehow recreate nature inside here. So that in itself takes a long time. And to mount the end station that we are using for introducing the sample to the region where it can interact with the light, it takes a team several days to prepare the environment that we are ready to do the experiments.
So you're both adding extra machinery to this already quite complicated setup, and you're preparing the sample.
Yes, a lot of the sample preparation takes place before we even come here. It can take several months to plan how to do it and to try multiple times to generate successfully a sample that we can actually use.
So I'm curious, what type of molecules or elements are in these samples in order to recreate nature?
Yes, part of the experiment is to find out what kind of molecules are in there. But part of our work is also to find ways that we can recreate nature in a slightly more simple form that allows us to get meaningful results, because nature is very, very complicated. So we want to find a way that we can make a model of nature to take to the synchrotron and then learn something about the model and then test our theoretical understanding with that model. And when we get to that point that our theoretical understanding matches what comes out of the experiment, then we can start creating an even more realistic and more complicated model of nature. So it's an iterative process. For example, one of the things we study is clouds. We would like to know what is the chemical nature on a very detailed level of the surface of the cloud droplets.
So you're creating small mini clouds when you're doing the samples, or do you have water vapor in a jar, or is it water samples?
Of course we have a lot of water, because clouds are mostly water, but they're not only water. Cloud droplets contain hundreds or thousands of different kinds of other molecules in the water. And the presence of these tiny, tiny amounts of molecules really affect how clouds behave in the atmosphere. So even if it's mostly water and even if it's water that create the cloud, it's all the little things that determine how white the clouds are, how warm they are they warming or cooling the climate, how long do they last in the atmosphere? Do they rain or do they just evaporate again? One of the ways that we found out that we can replicate certain properties of a cloud droplet is that it's actually not a drop, it's not a little sphere, it's a cylinder of cloud water. So it's mostly water, but it contains these tiny trace amounts of other molecules. And they are actually the ones that we are measuring inside the water cylinder that is our sample.
So what does that mean? It means that in your machinery you're spraying water while looking at it with the light from the...
Yes, in a way. We create, it's a bit like a water pistol. So we create the cylinder that is continually traveling, but it's very, very thin, it's very, very well defined, and it's about 20 micrometers in diameter. And it travels really, really fast. It's supersonic.
So supersonic, really, really thin water pistol.
Yes. That we are analyzing with a 32-meter long X-ray gun.
It is a bit noisy out here, and we can also hear in the background that people are coming out and working and doing experiments all around us. But I noticed there's a control room over there, so maybe we can go in there and find a bit more quiet to continue talking about your research and what it can be used for.
Okay, let's do that.
So now, Nønne, that we're in a slightly more quiet environment, can you tell me a bit about yourself and your background? How did you end up here?
It's a long story, full of many interesting twists and turns of coincidences. I'm Danish. I grew up in Denmark and I studied in Denmark. I'm from the island of Fyn, and I did my undergrad studies in Odense University. I studied theoretical physics and did a project actually on earthquake waves in geosciences. And for some reason, I happened to take a course in environmental chemistry with a younger professor, and it was very inspiring, and that sort of won me over for the course. And I knew about air pollution and climate change, but actually learning about it from a scientific point was, I felt that this was something really, really exciting, and I wanted to learn more. And later, when I had the knowledge, I felt like I wanted to contribute to it. And so I did my master's and PhD in University of Copenhagen. And after that, I had applied the research fund to do climate research in the context of chemistry. And I took that grant with me to Helsinki. At the time, it was called the Division of Atmospheric Sciences, led by Professor Marko Kulmala, and it's one of the biggest research groups in the field in the world. And then another coincidence led me to synchrotrons. A friend were in a conference and met some Swedish people that wanted to discuss about this kind of synchrotron spectroscopy where you could do really great things. And my friend is a theoretician and said, this is maybe not for me, but I think I know someone you should talk with. And one day these Swedish people showed up at my office and they explained to me that we have this method and we can do these things. And I was just sitting there, wow. And then I asked them, well, would you be willing to try this? And they said, yes, let's do it. And so I went to the old Max Lab and we did the first experiments. And during that set of experiments, we discovered something unexpected, and that led me down this road. And 10 years later, here I am.
Can you tell me about the unexpected thing that you discovered?
Yes. I was looking for evidence that when you mix organic and inorganic components that are representative of what can be found inside our little cloud droplets in the atmosphere, that the inorganics would be pushing the organics to the surface. This is a well-known effect. It's called the common ion effect. And I wanted to see if we could find evidence for it. And we didn't. But what we did see was that, yes, as completely expected, the inorganic components in the water pushes the organic to the surface. But then when the organic goes into the surface, it actually changes its nature, because the environment in the surface is so different from inside the water. And in hindsight, it seems very, you have this like, of course it does. But I think we had not really considered that, and I had not considered the effects of that or the implications that would have when it would happen in the atmosphere.
You mentioned the climate, and it's hard to think of a larger system on Earth to study than the climate. But then here at Max 4, you study those, like the surface of these tiny droplets and individual molecules on the surface of these tiny droplets. So what are the connection between this massive system of the climate and these individual droplets?
In 2 sentences. Let's see, how do we start that? Sometimes the smallest things can express themselves in very dramatic ways on the large scale. And I think it's extremely fascinating, and it's very, very difficult to trace the signatures of these tiny effects in the big system. But what we are studying is when we have these organic molecules in our cloud droplets that are sitting on the surface, it really matters how much they tend to accumulate at the surface, and if they sort of change their behavior on the surface compared to either in the gas phase or inside the water phase, inside the cloud droplets. It matters for, or we think it matters for, a number of different processes. And what we are doing here is trying to find out in more detail what is the expression of the behavior of the molecules when they're sitting on the surface of these cloud droplets. And then we take that knowledge, we quantify it as simply as we can, and then we try to create a theoretical model that we can then put into a climate model so that we can see in the predictions of the climate effect, would this have any effect? But this is something that happens long, long after we have been to Max 4. And it's a long project. That was 10 years before, I would say maybe 15 years before. And there will be many years after where we will be looking at the effects. But right now, what we have zoomed in on is that there is a number of different ways that the molecules express their properties on the surface that we want to study at Max 4. And then I have a whole team sitting back home that are working on how to take that knowledge and translate it into something that can also be described in a climate model.
And then I guess the effect in the model, in the climate models, can be things like, are the clouds dense or dispersed, or how many clouds are there, or things like that?
Exactly. It has to do with what kind of nanoparticles in the atmosphere form clouds, how readily do they form clouds, how stable are the clouds when they are formed, but also how big are the droplets that come out, because that determines how white the clouds are, and the whiteness determines the cooling effect of the cloud, but it's also related to then how long do the clouds stay. Because if you have a very white cloud that stays for a really long time, it's much more cooling than a dark cloud that only stays for a few minutes. And there are many hundreds of researchers who are working on having good models for cloud predictions in climate models. So we are also working with them, and of course we are building on the knowledge that they have spent decades on creating.
With all this data and the fact that this is a very long process, and at what point do we start to apply this? Or how old would you say the data is that we're applying right now to even understand anything about climate change?
This is a very good question. I would say that when it comes to climate change, we know what is causing it. So these are the greenhouse gases and predominantly carbon dioxide. When it comes to the clouds, the effect of the clouds is, in a way, it's cooling, so it's counteracting the warming from the greenhouse gases. And the reason it's so important to understand how the clouds behave is that this is the offset. And we don't actually know how big this offset is because it's highly uncertain. At the moment, a rough guess would be that the knowledge which is in the climate models is at least 10 years old. It's hard to say because there are many different climate models and you can run them with many different conditions. I did a paper before going to Helsinki. I had a short postdoc position at the Finnish Meteorological Institute where I did a study running a climate model with certain assumptions that I based on my PhD work. And we are starting to refer to that article, I would say, more frequently now. And this is almost 10 years ago that it was published. But this is just one example.
I know there's different opinions out there about how it's going. Is this good news, bad news?
That's another very good question, and it's difficult to answer. I would say the more we learn, it tends to be bad news. Climate is changing, and it seems to me that everything we learn is only that things are in less good shape than we hoped.
But your specific research, has that been good news or bad news? Like your knowledge of these droplets and how they change the climate models?
I would say we are still not, it's not completely conclusive. My gut feeling is that it's bad news in the sense that the cooling from the clouds in the atmosphere probably is stronger than we used to think, which means that we have a stronger offset than we thought. So that the effect of the greenhouse gases might be even larger than what we think.
So going into this, understanding that, that the climate is changing and that we need to do much more work on this, what do you say about the importance of the work for people who maybe don't understand the subject, or in fact, they just can't imagine how this can be happening now because they hear so many different sources of information?
Our work is a small piece in a very large puzzle of many thousands of scientists from the international community. We are all working on solving our own little piece of the puzzle, but we alone do not solve anything, but together. All of the different research group with all the different research ideas are trying to get their piece in the puzzle as correctly described as possible, so that when we put everything together, what we will get out of this is, I would say, the most reliable predictions of what will the climate be in the future, so that we can plan for it and that we can understand how the different processes interact with each other, so that when we act or don't act, because not acting is also an action, we can understand what will be the implications in different times in the future of those actions. This is what we're working to provide. A framework, so very large models that can give us these predictions with as high as possible confidence. And also, of course, not only the framework, but also making the simulations of climate in the future. And with my team and myself for many years' work, we provide a small module with a couple of numbers that we believe are as correct as they can get.
So you've mentioned several times that you work in a team, that this is a collaboration. Can you talk a bit more about that?
Yes, science is huge effort that takes place across time and space. We build our results on research that were done tens, hundreds, or thousands of years ago by other scientists. And we work together now with people in many different countries and many different fields. So I'm the head of my research group, and in my research group we have 3 different teams, and I'm mediating the collaborations between my team members. So this is our first or closest shell of collaboration. But then we have institutional, national, international collaborations with other research groups that are both doing the same thing that we are doing, but also that are doing different things, so that we can connect different pieces of the puzzle and make a slightly bigger section of the puzzle that we can sort of influence. And Max 4 is one of the environments where we collaborate with people, because we, of course, rely on all of the research and knowledge and efforts into building this facility. And now we are at this really privileged time where we can utilize this.
So it's almost like putting together a science rock band with different specialities.
Exactly. Somebody described that recently, and I think this is the perfect way of visualizing or describing it. I hadn't thought about it before. And also we like to think ourselves a little bit, it's nice to think of ourselves as cool.
I think you're super cool. So we started just outside with the beamline and seeing what it's like when you sort of start this process of finding out. So I was wondering if you could show me what your results look like. Like, what kind of information do you get out of doing experiments here at Max 4?
Yes. Now it takes a little while to open the computer. Yep. Then we get something like this.
Oh, so there's a graph, and it has just at the end there's a really high peak. So it's kind of a bit level. There's this few small bumps, and then it just shoots straight up into the air and then straight down again.
Yeah, they don't all look like that, but that's the specific fingerprint of these kind of molecules that here. So we shoot our liquid jet in, so it contains our molecules. Then we hit it with the radiation that kicks out some of the electrons from the molecules that are sitting in the surface. And then what we do in the experiment is that we collect these electrons and measure how fast are they. And from their speed, we can, and then knowing the energy of the radiation, we can then calculate what is the binding energy of these electrons when they sat inside the molecule. So you really get this very specific fingerprint of the molecule, and not only the molecule itself, but also its immediate environment. So for every compound, this combination of peaks will look different. And also, if you change the environment of the molecule where it's sitting in the surface, the peaks will also look different.
It's almost like shooting billiard with balls that stick a bit to each other. So you sort of calculate how much force you need to shoot a ball in a new direction, and then from that you can sort of interfere how they stick together and in what way.
So if you know the energy of your radiation, and then you kick out some electron, and then you can measure how fast is that, then you know how tight was this electron bound inside the molecule. And that is unique to that molecule. The experiments we do, we often know what kind of molecules we have in there, but we don't know the specific environment. This is more what we are looking at. And this is a stage in the process of understanding what is happening, because if we don't know how environment and identity interact with each other, and we just put in a real cloud, and there can be hundreds of different molecules, and we don't know how their fingerprints look on their own, we cannot say much. So this is why we start by putting in molecules that we know what are, and then we see how do they behave. And then we hope that in the future we will be able to measure on more complicated systems.
Great. I'm really looking forward to seeing how these pieces of the puzzle evolve and affect what we know about the world. Thank you so much, Nønne. It's been amazing talking to you today.
Thank you.
Thank you, and thanks for your interest in our work.
Thank you so much for listening to Intronauts with me, Toril Kornfeldt and Laura Raster. If you like the show, please leave us a nice review on iTunes.
And don't forget to tune in for our next episode when we talk with 3 of the employees here at Max 4. And we learn about what it's really like to work in a facility like this.